Okay, let's talk about standard temperature and pressure. That's often given the symbolism STP. It's a reference point for a lot of gas calculations. Don't confuse that with standard conditions for thermodynamics, though, because they're not the same conditions. The pressure is exactly 1 atmosphere, or 273.15 Kelvin. Avogadro's law says that the same temperature and pressure equal volumes of gas contain the same number of molecules or moles of gas. So if we set the temperature and pressure for any gas to be at STP, then 1 mole of a gas at that volume would have the same volume. We call that the standard molar volume. For an ideal gas, that volume is 22.4 liters at STP. In other words, it's a different way to measure moles. So if we look at STP and we have 11.2 milliliters, that's going to be 0.5 moles. If we got 44.8 liters, then we've got 2 moles. And so it's pretty easy when it's moles, but what if it's mass? So let's look at that problem beneath there. If we got 5.68 grams of oxygen gas, O2 at STP, we want to know what volume that represents. So if we look at this particular problem, we want to know the volume at STP. We're just going to add in our multiplication step here, and it's 32.00 grams of O2 per 1 mole. I just gave you the molar mass, but make sure, since it's O2, it's 32 grams per mole, not 16. A lot of people will mess that up. Oxygen gas is O2, not O. And then 1 mole of O2 is 22.4 liters. We see the grams cancel, the moles cancel, and I'm left with liters. And that means we would have 3.98 liters of O2 gas, represented by that 5.68 grams. Okay, let's talk about the combined gas law. This is a law for if you allow the pressure, the volume, and the temperature to all change at the same time. Because a lot of times that will happen. We can talk about situations where it kind of works, where it's just the pressure and the volume change, but the temperature stays the same, for example. But that's certainly not all the time. You could imagine a condition where they would all change. So if we compare Boyle's law, P1 V1 equals P2 V2, and Charles's law, V1 over T1 equals V2 over T2, we realize that the pressure, volume, temperature all have a proportional relationship going on, so that we can say for a given gas, under a given set of conditions, pressure times volume divided by temperature equals some constant, which we'll call K. So if we set two different sets of conditions together, we get P1 V1 over T1 equals P2 V2 over T2, which is our combined gas law. So if we look at a problem, we got a sample of nitrogen gas N2 occupies 750 milliliters of volume at 75 degrees Celsius at a pressure of 810 torr. What volume would it occupy at STP? So there's our standard temperature and pressure again. That is going to tell us the temperature and the pressure under the final conditions, and we'll only need to calculate the volume. So don't think you don't have enough information. The STP tells you what you need to know. Okay, I've transferred the data from the problem text, and the STP conditions for the second is 760 torr because STP pressure is 1 atm, or 760 torr. The temperature is 0 degrees Celsius, or 273 Kelvin, and we're trying to solve for the V2. We'll need this in Kelvin, so add 273, and we get 348 Kelvin. Now we need to solve this for V2. So V2 equals P1 V1 over T1 times T2 and P2. We can arrange the variables a little bit more logical way than that. So that's going to be V1 times P1 divided by P2 times T2 divided by T1. Then we can plug and chug. 750 milliliters times 810 torr, 760 torr. Doesn't matter what the units are as long as they match, because they are going to need to cancel. Just the kelvins have to be there. And so it's going to be T2 is 273 Kelvin, 348 Kelvin. So V2 then is 627 milliliters. And that would be our answer. We've talked about changing conditions on the same gas, but what about one gas under one set of conditions? How do I do that? That's where the ideal gas law comes in. And so if we take some of our proportional laws, we can come up with a formula for one set of conditions. So if Boyle's law, the volume is proportional to 1 over the pressure at constant temperature and amount of gas, where N is going to represent the number of moles of gas. Charles's law is equal to the volume is proportional to the temperature at constant pressure and moles of gas. Avogadro's law said that the volume and the number of moles of gas were directly proportional at constant temperature and pressure. If we combine all of that, we say the volume is proportional to the moles times the temperature divided by the pressure. If we insert a constant of proportionality, which we'll call R, and we can make that an equal sign. So V equals nRT divided by P. Or we can slightly rearrange that to give us the gas law as you're used to seeing it, PV equals nRT, where R is that proportionality constant. We call it the universal gas constant. We did a version of that when we saw it in thermodynamics, but we're going to use a little bit different version here. So if we have pressure in ATM and volume in liters, and of course gas, or the temperature of the gas is in Kelvin, if we look at the R constant when you have 1 mole of gas, so we plug in, so rearranging for R is equal to PV divided by NT. So that's going to be 1 ATM times 22.4 liters, because that's the molar volume of a gas, divided by 1 mole and 273 Kelvin. We'll get a gas law constant of 0.0821 liters atmospheres per mole Kelvin. And that'll be the version we'll focus on for this chapter, so you'll want to know that constant. R can have other units, however. In the thermodynamics chapter, we used 8.314 joules per mole Kelvin. And there's some reasons for that, but it does end up working out unit-wise. If you did millimeters of mercury in milliliters for the pressure volume units, you get 62,400. If you're working in a particular set of units all the time, you might get an R constant for those particular units. But without that, you might as well just use the units you got, use one R constant and not convert your R every single time. That'd just be too much work. So we want to know what volume with 50 grams of ethane, C2H6, occupy at 140 degrees Celsius at a pressure of 1820 torr. The only reason we need to know the mass of the gas in this case is because I gave you the formula, and we need that to get to the moles. Otherwise, you don't really need it. Okay, to make this work, we're going to work through several things. First, I need the moles of the gas and not the mass of the gas. So, molar mass of the compound is 30.08 grams per 1 mole. And that's going to give us 1.66 moles of gas. I need that to be able to work the problem. If we add 273 here, that's going to give me 413 Kelvin. Then I need to convert that pressure. And there's 760 torr per 1 ATM. So that's going to give me 2.39 ATM. This molar mass I just added up in advance to save us some time, but you can go back and prove it to yourself. Now I'm ready to plug in. I want to solve for V, so V equals nRT divided by P. And so that's going to be 1.66 moles. The R is that constant we were just talking about, 0.0821 liters ATM per mole Kelvin. And then the temperature is 413 Kelvin. And we're going to divide that all by the pressure, 2.39 ATMs. But we see why the units have to work out, because they have to cancel with the units in the universal gas constant. And so the volume when you're done is 2.36 liters. And that would be our answer.